好的，各位贵宾，大家午安哈！我是德瑞达科技的 Peter 邱云瑶。那今天很高兴在乔悦的摊位上能够介绍来自于瑞士的一个非常精微微细的一个 Micro 3D Printer 的一个技术，它叫做 SiP。那它所推出的叫做 Micro AM Solution，它是现在目前世界上最细微的一个商业化应用的 Micro AM 金属的一个微细的 3D 列印技术，它可以做到纯金属，而且细微度可以在1个 micron 之内。那不管今天是要在晶圆上，或者是在金属的基板上做微细的加工，它都可以做。好，那今天为我们做演讲的是来自于S 档公司的那个行销部的企划的人，叫做 Edward White，Mr. Edward White。So 那我们现在就把时间交给 Edward White。OK，yeah, Mr. Edward White，please go ahead your speech and to introduce your solution come from Aston, Michael AM. Thank you. Yeah.
Thank you, Peter. Hello, everyone. Thank you for taking the time to join us today. My name is Edward White. I'm the marketing manager at Exodon here in Switzerland. And so today will just give you a brief introduction into Exodon as a company, our technology, the types of objects we print, their properties, and the use cases and the functionalities that we have developed and how that applies to the semiconductor industry. So Exodon was formerly part of Cytosurge, which is a biotech company here in Switzerland who developed a very well-renowned technology called Fluid FM. And it was previously a business unit of that company, and we developed into this standalone business focusing purely on the additive micromanufacturing of metals. This has been a business unit that's become its own company because there is so much demand for it, and we see it being such a promising technology. And so we have ongoing research collaborations with various premier academic institutions such as ETH in Zurich, EMPA, the Swiss Federal Material Science and Technology Institute, and also FBH in Berlin in Germany. And so our core technology we call Ceres, which is a unique printing technology. It is a standalone system, as you see on the left here. No need for a clean room. You can just have it in your lab, and it prints at room temperature using a very, very localized electrochemical deposition. And so the Ceres machine is capable of printing fine lines in 2D and also 3D structures out of metals. And it prints using this electrochemical deposition method through what is in essence a hollow AFM cantilever tip. And we print what we call voxels in a layer by layer sequence within an electrolyte bath, and horizontal prints are possible with this system. And this is a really unique system, and we see it having unique application. It's a system for innovators and visionaries who see what additive micromanufacturing can do for their use case. So we conducted a competitive landscape analysis within the world of micro-scale additive manufacturing. And whilst there are people printing polymers at a similar size range to us, there is nobody that we have seen who is able to print metal complex objects out of metals in the same size range as us. And so this really is a unique technology with unique applications. Research is very important to us, and we are well integrated into the science community. We have frequent publications in high impact journals, and we focus on an ongoing cooperation and collaboration. From before we spun off into a separate business, we had publications in key journals, and we're continuing that now. So we print using electrochemical deposition, and in theory, anything that can be electroplated can be printed. We see particularly copper and gold as being the key metals, and that's what we focused a lot of time on. Copper specifically in the microelectronics industry. And so we print on substrates, as it is electrodeposition, and primarily we focused on copper, gold, and flexible polymers such as PDOT. One of the key aspects of our technology is that we operate at the microscale. So as you see in the smaller image, we are able to print nanopillars which have a diameter of only around 200 nanometers, all the way up to our version of Michelangelo's David at around 1,000 micrometers. And so what the beauty is of our system is that the size of the minimum features of a given printed object can be changed whilst printing without the need for a different printing tip. This is all through tuning the diameter of these voxels that we print. And so this being tunable on the fly means that the user can customize what they're printing without any changing of tips. At the microscale, accuracy is very important, and uniformity and repeatability is very important, as it should be for a mature technology such as ours. So on the left here, we have 1,600 micropillars printed in a 1x1 millimeter grid. Each pillar is around 1.6 micrometers in diameter, just as a test to show the repeatability of our system. And this can go up to these hexagonal copper microchannels printed on PDOT on the right there, which, as far as we are aware, is only possible with our technology. As I mentioned before, our Ceres machine offers tunable print parameters on the fly. So in these images, each of the strands in a different color is a different diameter. And this is changed whilst printing in a layer by layer sequence. And this just wouldn't be possible if we weren't able to toggle those parameters. And this is a really key feature of this technology. So our machine prints at room temperature, and it doesn't require support structures, which is very unique within particularly metal additive manufacturing. And so the top image has got an aspect ratio of about 100:1, and this is entirely self-supported, and you see in the lower ones 90-degree overhangs are possible, and there's no need for support. Coils are typically difficult for additive manufacturing in metals, and we've produced a whole range of them in different sizes, such as the large center one here for Harvard Medical School, down to overhanging ones on the bottom right, or on the left here with the flat top above it. More examples of what our Ceres machine can produce here is these lattices. On the left is the representation of the object in our software interface prior to printing, and on the right you have the physical realization of it. an example of an industrial use case here. This is a microplug for medical usage. On the left is the real size of the existing product, and then on the right is what we were able to produce for this company over 3 times smaller and in a very complex coil design, 3 times smaller than they originally had, and in a way that only our technology could produce. And so our Ceres machine enables a wide variety of possible geometries of these metal objects, from coils to lattices, hollow volume objects, and the layer by layer deposition enables these overhangs to be printed without the need for support struts or any post-processing. Crucially, the mechanical properties of our metal objects is very sound. So in mechanical hysteresis testing, we can see that the printed copper is very elastic, it's mechanically stable, and there's excellent adhesion to the gold substrate. In terms of the material density, we've achieved over 99% density of a solid copper print, as can be seen here through the FIB slicing. We can see the homogeneous grain structure. There's no trace of individual voxels anymore. And the conductivity of printed objects is very good. Taking away the copper to gold contacts, we're achieving conductivity close to that of bulk copper. And so a key part of this Ceres machine is the accuracy of the system. So taking a traditional manufactured object such as a MEMS device, say the user needs to connect 2 contact pads, as we see on the left here. Using the inbuilt cameras in our machine, within our software interface, the user can digitally position an object they need to be printed with micrometer accuracy. And so they position it and then they print it, as we see on the right here. Now, this being an optical system, this functionality is optical, the limit of accuracy is around 4 to 5 micrometers. And for really accurate work, we want to develop something which would better this. And so we worked on developing what we call a mapping functionality. And so this functionality, the mapping process, is to map the surface topography of existing structures, and to do so with sub-micron precision, beyond optical resolution, which we already have. And so as we print using this ion tip, which we see in the left image here, we used that to conduct an AFM style tapping of the surface to generate data of an existing structure, and we use our print software to then create a visual representation of what the tip has interacted with. And we want to use this so that we can map a pre-existing structure and then print on it whatever print object we want or the user wants, and do so with sub-micron precision. And so some examples of this, say the cross on the bottom right here, our tip is approaching it, it is interacting with this pre-existing structure, and the software is generating this map. And you can see here on the right that the map generated is extremely accurate for each of these structures. And so from map to object location, we have the existing structure here on the left. And so the tip interacts with these, and each time the tip touches it, it deflects slightly as per an AFM, and it produces, it gives data to our system, and using our software, we produce a visual representation of this. And the user is given absolute and relative coordinates of a given structure. And given that they then have that, they can print all in one seamless workflow at a location on that structure with sub-micron precision. So to go through this example here, we have this sort of cross structure on the left. The tip has interacted with it during this mapping workflow. We get this representation of the surface, which has been mapped, as you see in the second image. And then in the third one in the middle, we see the coordinates right in the middle of this existing structure. And so choosing a print location, which is entirely down to the user, within this map that the software has generated, they can choose an extraordinarily precise print object location. And so we produce this micropillar in the center of the cross, which has a diameter of around 500 nanometers. The map that is generated is also customizable by the user. So we can, if I'm the user, perhaps I want a map of 40 by 40 micrometers with intervals every 1 micrometer. I can choose that. Perhaps I want a larger map. It depends on the surface that I want to map, but essentially it is all customizable by the user. And given that this uses our existing print logic, this happens rapidly. And so we've developed this because we see it being extremely useful, particularly in the microelectronics industry. Some examples here of our use cases: high frequency technologies such as receivers and waveguides, neuroprosthetics such as electrodes, watchmaking, and custom bespoke items such as for copyright, microelectronics such as the plug mentioned earlier, and certain connectors, and then of course the semiconductor industry. And this mapping workflow we see as being really unique and directly applicable and relevant to modification of existing structures on semiconductor dies. Whatever that may be, the user can enable this functionality to obtain a super accurate representation of a structure and then print on it with accuracy at the level of less than a micrometer. So that concludes the presentation for today. If you're watching this in Taiwan, then I urge you, if you would like to know more or to collaborate in some way, to speak to the guys at DETEKT. If you're watching this after and you're in Europe, then you can contact us directly. But essentially, we can collaborate on all sorts of applications, and we'll be very happy to speak to you. Thank you for your attention, and I hope this has been informative and interesting, and I look forward to hearing from you. Thank you.
Okay, thank you. Thanks, Edward. It's quite a good presentation, and I think we can collect some questions from our customers.
Yes.
Yeah. Do you have any question? I think I have two questions. The first one is that from now on we can print a couple silver as well as gold on the substrate. The
Yes.
substrate have need to plating the conductive layer.
Yeah.
What kind of the material of the conductive layer?
Well, as you say, the substrate needs to be compatible with electrodeposition. It is possible. It depends on the chemistry of the interaction of certain elements, but we can actually cover the substrate with a certain layer or film if necessary, which can later be removed with etchant or isopropyl alcohol. So there is actually there is some possibility and leeway in that realm. As we print in a specific chamber, which contains electrolyte, we just need that connection to the substrate in order to print. But specifically, what that top layer is, there is some freedom.
Okay, so do you mean the we can deposit the conductive layer on the top? So in case of the if we are going to deposit the polymer, can we deposit the polymer ink through the micro AM nozzle?
We can print 2D in liquids and some polymers, but we're focused on depositing metal in 3D.
Okay.
So
it is possible.
Yeah, what we're focused on is applying a pressure through this printing tip and delivering ionic metal solution, which is then reduced into solid metal atoms within the electrolyte bath upon the substrate.
Okay, sounds good. The second question, I asked the question on behalf of our customers. We saw the colorful structure, microstructure you have.
Yes.
On your slides, it is colorful. So what kind of how can you reach the colorful microstructure like this? You know what slide I'm going to. Yeah,
Yep.
Can you go back to these slides?
Yeah, absolutely. If you mean specifically the color is merely a graphic representation, so anyone viewing it, looking at these images, can see distinctly that the diameter of those strands is different. The structure is just printed out of copper, so there is no color aside from the copper. It's just that we edited it after the fact in the image so that anyone viewing it can easily see that the strands are of different diameter.
Oh yeah. Oh, you dye the color.
No, just in the image.
Just okay.
Just the picture
Yeah.
is different. It's we're not able to colorize the individual copper strands. That's just purely for the publication, so that readers of that article can see that the strands are of different diameter.
Okay. Edward, can you go back to the previous slide? Yeah.
This one?
Oh no. Previous. Yeah. The previous. Oh yeah, this one.
This one.
No, next one.
This one.
No, next one. Oh yeah, this one.
Yeah.
It is colorful.
Yeah.
So just the image of the marketing.
Yes.
Okay. Wow, fantastic. We never seen that. Daniel, do you have the visitor raise the question?
No.
Okay, thank you. Yeah, Edward, very nice presentation. Yeah.
Thank you.
Yeah. We just ended the section. Thanks for everyone your time and your contribution. Yeah. Thank you.